further ado, Dr. Castillo.
Good morning. So I'm going to talk about computer simulation and robotics. And these are two things that might be a little separate, and I'm going to try to tie those together for you guys, mainly because our movie today is about robots. It's Robot and Frank. It's a fun movie. Little language here, but it's really a fun movie about a robot that is helping this old guy because he's starting to have Alzheimer's, and he's, it's a social thing, and so it's a really fun movie. And I want to talk. My focus is using computers to solve problems, and at the lab we have the largest supercomputer in the world, the most powerful computer in the world. So we use the computer a lot to solve problems. So, as I mentioned, the two topics that I'll be talking about is computer modeling and simulation. And you guys are familiar with that? Anybody familiar with that? A few people are. Using computers to simulate things. And robotics. And how I'm tying this together is I'm going to talk about each of these, why they're important to us and to scientists, how they're related, and how you guys can start with both of these, both the robotics and the computer simulation. And so we're all familiar with robots in popular culture. I'm sure you guys recognize most of these. Show of hands, most of them? Yeah? You guys know Data? What's this one? Right. How's this guy? You got the movie? RoboCop. This one? Yeah, I just saw that the other night. It's a great movie. What about this robot right here? Metropolis. Yeah, that's a real old movie. Yeah. So it's been part of our popular culture for a very long time in the movies. Also, computer simulation has actually been part of our culture. Look at Star Trek. Star Trek had a very powerful computer. And every time they got into a little trouble, they would go to the computer and say, "Computer, analyze this, tell me that." And the computer had to kind of think about the problem, run some simulations, and come out with a advice for the guys, for Captain Picard or Kirk or whoever was on the Star Trek, whatever episode you were watching, whatever season you were watching. And so, why is computer simulation important? You guys have some suggestions? That's very good. He says less expensive than actual testing. That nails it right there. Here's an example, and all these are projects I've worked on. Here's an example of a jet engine. And so with this jet engine, we can model this jet engine, all the mechanics of it, how the metals interact. And then we intentionally sever one of the impellers and watch it go flying into the shroud. Now the shroud has to be strong enough to keep that from happening, keep that from going off and hurting somebody, injuring somebody, or damaging the rest of the plane. But it also has to be light enough to fly in an airplane. And so that's one of your engineering design constraints. You can't do that experiment. It's too expensive to do that experiment. It's too dangerous to do that experiment. Modeling things that go super, super fast, that fly through the atmosphere at 8 to 12 times the speed of sound. That's hypersonic fluid dynamics. Car crash simulations. We can model car crash simulations, or we can model car crashes. We understand the materials, how the materials deform, the rubber of the tires, the metal, the glass, how everything reacts. So we or Detroit can do car crash simulations they can do these simulations in the computer. They don't have to crash cars, which is pretty expensive. They still crash a few cars, but they don't have to crash as many cars now because they can use computers to do this. Even the crash test dummies are simulated now. So they're putting crash test dummies out of business. And so how does simulation fit into science? Originally the early scientists, they started by doing observations with their eyes. They started building instruments to see even stronger to make better observation using computers to collect data. And they captured all this in theoretical laws, in the language of mathematics. So it used to be that if you're a physicist, people would ask you, are you an experimentalist, or you're a theorist? But now there's a new kind of physicist called the computational physicist. And the computational physicist does a little bit of both. They take all the theory and they capture it in the computer. And they run a bunch of experiments with this now. And so now they're doing experiments, but they're using all the theory combined together. And so we can use computer modeling and simulation to do a couple of things. We can make predictions, like the weather prediction. The weatherman always has their models, their computer models that they're looking at. And they have several of them, and they're trying to figure out what the weather is going to be next week based on these models. We can understand a complicated system. We can start to put pieces together in the computer and watch how things interact. And we can do a lot of what-ifs. And we can start to build our own intuition on those complicated systems without actually having to build them. Sometimes they're impossible to build. And we can learn a lot from those. And another thing that we can do with computer simulation is we can use it for communication. We can use it to communicate very complicated ideas. So I want to give you an example of that. So for example, the designing of a house. If you're going to design a house to be very thermally efficient, not requiring a lot of electricity, you might think about how to design these eaves so that the summer sun is blocked out, but the winter sun can come in and warm up the house in the wintertime. And you might have these nice clear-story windows that allow the hot air to come out in the summertime, but trap it in the wintertime. And a good thermal mass to keep that heat from the day during the night, or the coolness for the day. And so we know that 1/3 of the U.S. energy consumption one-third of U.S. energy is consumed by buildings. And so if we can make buildings more efficient, we can actually save a lot of energy. So a young high school girl named Kira wanted to do a project on this, a science project on this. And so Kira wants to be an architect. And so she was very impressed when she went to Zion National Park and saw their interpretation center, which was very thermally efficient. And she brought home their model, which was in a brochure. It's just a 2D drawing, but this is their model of how that building works, why it's efficient. She went on to put this in Google SketchUp and made a 3D virtual model of this building. And then used a laser cutter to cut out physical models of this building to start to understand it. Then she put different kind of roofs on there to understand what happens if you have a white roof or a black roof or this green roof, which is kind of represents grass. She used a heat lamp to represent the thermal loading from the sun and instrumented it. But then we went a little further. I helped her on the science project. And we built a computer model of this. And so when I hit go, we have different things going on. So what do you suppose these yellow rays are? It's the sun, yeah. And the red is heat. It's heat being reflected. The light, when it comes into a colored roof, does a couple of things. It can heat up that roof. It could be reflected by that roof. It could be transmitted to the air inside and heat that up. So this is like the air being heated up. And that gas, when it's heating up, it tends to rise up and it can come out this window right here. But also, we can have infrared coming off of the roof from the heat underneath it. So all this stuff is being captured. And then, so this is capturing a lot of these ideas. Now let's do some what ifs. Can we explore this system? Let's do something like let's close that window You see how that window closed up there? I see I can open and close it. Let's close it. Let's change the roof color to be really dark, like some of these roofs that we see around California. So what's happening now? Yeah. Less of the sunlight is reflected, and it's being absorbed, and it goes into the living space. The temperature becomes higher, and now we're at a point where we need to turn on the air conditioning because it's not so comfortable anymore. So let's do another experiment. What if we change that roof color to be really light, like they do in South America and the Mediterranean? And let's open that window. Let's make some wise architectural choices here. And so now we see that most of the light is being reflected away. Very little is being transmitted into heat. A lot of the particles, or a lot of the heat, can escape through there. And we see what happens to the temperature. It's a lot more comfortable. It's a much more livable architecture, living unit. We don't have to use as much electricity. Now, so this model is probably not what you're going to use to design a house. It's a little bit of kind of a toy model. But Kara, who wants to be an architect, can use this model to go to her clients and explain some very complicated ideas. So this is how we can use simulation as a communication tool. She doesn't have to be a computational physicist. She can be an engineer, an architect. She can be, any type of professional can use computer simulations to communicate complicated ideas. And so at the Livermore Lab, as I mentioned, we have the most powerful supercomputer in the world. We're building, every year we're going to build another, or every couple of years we build it more powerful. We keep up. We're keeping up. And let me show you a couple of examples of some of the work that we do. And it's kind of flashy. I put some music to this, which we can really crank up sometimes. So this shows the dislocation in crystal structures. This is the aerodynamics of trucks. We can actually improve the efficiency. This is a turbulence done resulting from different density materials coming together. This is ion transport. This is neutron transport from our National Ignition Facility being modeled. You guys know what this is? Yeah, we're modeling earthquakes actually on the scale of the Bay Area, trying to figure out where the energy is going to end up. This one, anybody? This is a instability when you have it's called a shear instability when you have fluid going over a surface. This is the reason the flag flaps like that. It's that shear instability. So, I talked about computer simulation. What about robotics? Why are robots important? Anybody have any ideas on that? They can cook for us. So here's some images I just grabbed off the web, just kind of showing different applications of robots right now. And so I showed how does computer simulation fit into science. So how does robotics fit into engineering? Well, in engineering, traditionally there's a couple of main branches of engineering. One's called mechanical engineering. And in mechanical engineering, you're thinking about forces and torques and structures and gears and how to make things move and transport energy. Electrical engineering is more about circuits. How to make things, how does electricity flow? How do computer circuits work? How do logic gates work? And so these are two traditional forms of engineering previously. But they've been combined in something, sometimes it's called robotics and autonomous systems. Sometimes it's called mechatronics. So you can go, like UCMR said, they have a big mechatronics effort. and you can get your degree studying both the mechanical aspect of things and the electrical aspect of things with a goal of making big fat robots like this, or robots that can help. Question? That's right. Big Hero 6. And so robots do a couple of things that are important for us too. They do boring and repetitive tasks. They do the same thing over and over again that we don't want to do. Cut the lawn, make a car. Different things that aren't so good for humans to be doing. They can do dangerous tasks. They can do rescue operations in very dangerous environments. And again, like computer simulation, they can be used for communication. I think right now, these robots that are called telepresence robots, which are really a robot moving around with something like an iPad, are one of the biggest pushes this year for robots. These are the biggest commercial robots available to us right now, are these telepresence robots. If you guys ever go to the Maker Faire, you'll see a ton of these things running around. And there's a person on the other side. The person could be on the other side of the world. And this thing's just going around and it's interacting like it's a person. And I'll demonstrate one over here. And so let me give you an example. And I'm going to have to go to the web here and show you a video of Tesla cars being made. And if you go down to their factory in Fremont, you'll see a lot of robots. They have about 500 robots and only about 3,000 people, auto workers. And I think it's going to be, in the future, probably the other way around, probably about 500 people, as far as on the manufacturing floor. All the other people, tons of people are doing design and robotics. A lot of the jobs are doing more technical things, not just welding and putting things together. So that's the Tesla car being manufactured. And they do pretty much everything. They just carry the car around and to different stations, put the different parts on it. Let's see. And so there's some other cool robots. This guy's really cool. This guy's called the Now, and I think we have time, so I'll show you a little quick. I have a friend that has one of these. They're commercial. You can buy them. They're about $15,000 right now, but they're coming down in price. They have the ability with different kinds of cameras to localize where you are. They have several microphones, so they can do facial recognition. He recognizes who that is. Can track the person, recognizes where a person is. If you say something, it knows where you are. Like we have two ears to figure out where the sound's coming from. A lot of good balance capabilities. So these humanoid robots are really coming along. The programming for this guy is done much by just moving it, telling what you want it to do, instead of having to code every little thing like how to move the fingers and joints. And so now it can do things like catch a ball with a little training like that. So I wish I had one of these for the demo, actually. I'll show you what. So he said, come here. It was able to figure out where here was based on the microphones. In case the floor changes, it can change the walk to maintain very good balance. And in case of a collision, We'll show a collision in a second.
That's not really fun.
So here's a collision. It actually pulled out its hands to block, to hold the floor, to block its collision with the floor. So there's a ton of things on the web to watch. We could spend all day doing that. And so what I like to talk about is in the category of mobile robots, and I have a robot up here that I'll demonstrate for you guys. And just to show you what it is, it's a hacked Roomba. A Roomba is something that vacuums your floor, but we hack into it with a laptop, and we give it a pair of eyes, which are done with Microsoft Kinect. The Microsoft Kinect has the ability to see color and 3D, and so I will fire this guy up. Let's see. I need to unplug it here. And bring up one of the... Takes a little second for it to boot up real quick. So the laptop for this is just a very simple... it's a very simple netbook, not a very powerful computer. But I'm going to upgrade that pretty soon, and I'll talk about that in a second. And it's too bad you guys can't see all the stuff that I have access to, because it has a ton of... It connects up to a lot of different parts of the robot. Sorry. This part usually takes a little second to do. So let me talk about the Turtlebot team first, while I'm booting this guy up. So the Turtlebot team, we have, it's an all-girl high school team, and we program the robot to do a bunch of different things. And, and maybe rebooting is one thing that... Oh, I see. The Turtlebot was off. So, there we go. That's better. And so what we do is we actually use simulation here to have the Turtlebot move from point A, where it starts, to a target. And then we can randomly put in obstacles and have it move around in the simulation, and then we program the robot to do exactly the same thing. Okay. What I didn't do is bring my daughter, who is usually my robot wrangler. Okay. Okay, sorry about this. Okay, so let me go into the simulation real quick. Well, this guy. So this is a simulation that's actually written by one of the high school students. And as I mentioned, we have to get the robot, the Turtlebot, from this point to this point, which is pretty straightforward under normal circumstances. But let's say we draw some obstacles in the way. So I can use my mouse to put different random obstacles in here. and then I can hit go. And so what we're going to see is we're going to see the robot moving forward, and we're going to see the vision cone that it has, which is from the Microsoft Kinect. And since it only has a 57-degree cone, it actually has to turn as it moves in order to scan all the obstacles. And so when I hit go, we will see it try to get to the obstacles, or to the target. And that gives me a chance to reboot the robot. So you see how that worked? So I'm going to try it one more time. Try to make a really difficult obstacle here. Okay. Okay, I will try to get this running for after the show. So what I promised to do is tie computer simulation and robots together. And so how are these related? Can anybody see the connections that I've made between simulation and robotics? Any guesses? How simulation? Yeah. I'm sorry? Both. They do. They make things easier for us. What about doing things that are dangerous? That's another example. Here's another connection between the two, and it's not an intuitive connection because it has to do with this scientist who did his work in the 1960s, and he postulated that computers are going to get cheaper and faster exponentially. And he started collecting data. And this is the data he collected between 1960 and 1965 about how fast computers are getting, how cheap they're getting. And so he predicted computers will continue along this trend. This is his data. This is his projection. And you can see this is what history has shown us. So he was pretty close. I think he was projecting out to here, but computers have been getting faster and cheaper. And it's not just the supercomputers. It's most of the commercial products we use. Anybody recognize what this is? It's a cell phone. Yeah, a few of us have probably even seen a cell phone like this. It's a 1978 cell phone. It cost about $3,000. It did one thing. It made phone calls. And compare it to this thing right here. Anybody know what this is? It's a computer, right? It's a computer that just happens to make phone calls. It costs about $300, $400. It has almost a gigaflop of processing power. That is more computer power, more computational power than was used to put a man on the moon. And we play games on this, right? We play the Angry Birds and stuff like that. So the thing is, if Moore's law continues, and we expect it to continue, we're going to have very, very fast processing power in our pocket. This is the computer. This is a supercomputer at Livermore Lab. The current supercomputer that's being replaced, it's 16 petaflops, which is about 100 million times faster than this computer. If things continue, that kind of processing power is going to be in our pockets in a decade or so. So if you're not comfortable using computers to solve problems, you're going to be left behind because other people will be using computers to solve problems. So that's kind of been my message about this. Now, computers are used for two things that I've been talking about. Obviously, computational simulation, but also making robots smarter and faster. This is our next supercomputer. This is one we're building right now. Sierra is being built out of graphics cards. NVIDIA graphics cards, literally. We're partnering with NVIDIA to make the next fastest computer in the world. That's because those little GPUs, graphical processing units, are cheap and fast. In fact, NVIDIA sells this board right here that has 192 processors on it. And they sell it for $200, and it runs on 5 watts of power. 5 watts. A hairdryer is like 1,000 watts. But this thing runs on 5 watts. And now you can power very good computers with that. In fact, that will be the next version of Turtlebot here. Maybe one that boots faster. And so, how can you start? This is one of the points I wanted to make. How you can start, and you could start by different ways. We first of all we have the Teacher Research Academy, where we bring educational resources to teachers. We do a lot of teacher professional development. One of our teacher professional developments at Livermore Lab is teaching them about computer simulation. We also are bringing that to CSU Fresno this year and Cal Poly. The San Joaquin County Office of Education is using some of the stuff that we're teaching about, some of our content, to teach 58 teachers over the next 3 years. This is actually year 2 of that program. And as I said, we've had it at Cal Poly and UC Merced, and we're bringing it to Fresno State. And this is the software that I like to use for that. It's called NetLogo. And NetLogo, you can download it for free. You can, it runs on Macs, PCs, Linux boxes, and you can get started. It's really friendly. We've had courses to teach 5th graders how to use it. Yet we can bring it to the university students can use it. This is the software Kira used for the architectural simulation. This is what we use for the Turtlebot simulation. So it's a very, very easy to use, free, and robust. It was developed by a guy named Seymour Papert, who created, he created the Logo language, and then NetLogo is a modern version of that. But he created this for educational purposes, but back then the computers weren't fast enough to really do cool problems. Now they're fast enough to do really cool problems with it. And so robots, if you want to get into robots, you can build a Turtlebot. You can download the Robotic operating system, which is free and open source, and start playing around with that. The Turtlebot runs on ROS. So does this $450,000 research robot at UC Berkeley. So this $450,000 research robot is being trained to do a very dangerous task right here. Anybody know what that dangerous task is? It's folding a towel. It's actually doing the laundry. If you look back here, there's a washer and dryer, and the robot can actually do the laundry. So I don't know if this I don't know if this falls under dangerous task or repetitive task, both. But it's something that people don't really like to do. Now, it's not like they have an idea of using a $450,000 robot to do this. This is an experimental robot, and so they're looking what is needed to fold laundry, which is not actually an easy problem to fold a towel. The thing has to look down, has to figure out where the ends are, and calculate how to fold it. It's funny, a friend of mine at Sandia designed, when he was at Willow Garage, designed the optic systems. He put $30,000 of the most expensive optics into this robot because he wanted this to have the best vision ever. Well, they disconnected this at UC Berkeley, and they put a Microsoft Kinect on top. And the Microsoft Kinect was sufficient for what they needed to do. And the idea for them is they wanted to make the lowest cost available. Lowest cost robot available. Something else you can do to start is learn about Python. You can download IPython. Lots of good scientific applications there. It's probably the most used language at the Livermore Lab. It's Python. And you can do these notebooks and learn a lot. And you can connect up with cool hardware like the NVIDIA developer board or this BeagleBone or Raspberry Pis or Arduinos. And you can train them. And now you can bridge the computer. You can start doing robotics with this. Okay, so what we covered here today is that, in my opinion, computer simulations and robotics are going to be super important tools for the next 5 or 10 years. And what we did is we talked about why they're important. Anybody ideas? Why are they important? Save money. They can do laundry. How are they related? Anybody? The computers getting cheaper and faster. And how you can start. You can download NetLogo, start doing simulations. You can, and if you guys want some demonstrations of that, I'll be glad to demonstrate that during our question time before the movie starts. And there's also the robotic operating system, and there's a lot of ways you can start with that. And so now I'll take questions. Thank you. Any question right there?
Oh, I just want to see the simulation.
Okay. Any particular topic?
No, whatever you see.
Maybe somebody can suggest a topic, and we'll try to find something. Question here? How frequently robots are used in surgery? More and more. In fact, that's probably the biggest investment right now in robotics is surgical. And it used to be that presently robots are used as telepresence robots, where there's a doctor on one side, and he might be on the other side of the world, and he's doing something with gloves, or he's actually controlling a robot somewhere else to do surgery. And that's kind of a telepresence type of operation. They're getting more into having the robot make its own decisions, and because a lot of times the robot can even think faster than the human with some of the in some cases. There was another question.
Yes. How about the interaction with the rock, the solution?
How for the simulation?
Yeah, no, the material product.
I'm sorry, for the
The chemical.
chemical? Oh, yeah. Yeah, so how are simulations used in the chemical? How effective? Yeah. So about the pollution and stuff like that in the So simulations are being used quite a bit. And the question is about how the pollution is being modeled, simulated. The chemistry going on in the atmosphere is extremely complicated, and it's complicated by different chemicals, different atmospheric conditions, having light come in, and light affects chemistry quite a bit. And so we have very simple models, but now we have to use computer simulations to actually make them more complicated and actually investigate a lot more. So there's quite a bit in that. Any other questions? Oh, yeah. Yeah, so thoughts on cars driving themselves. So, in fact, Elon Musk gave a great talk at the NVIDIA conference last week, and he was talking about this. He says some of it is trivial, and some of it's very, very hard. He says, like under 5 miles an hour, you can program a robot, a car, to drive and not run into anything. You know, it'll stop, it'll move around. That's the easy thing. On freeways, at freeway speeds, at high speeds, it's pretty easy too, because there's general rules. Things are fairly confined on your freeway. It's the in-between. It's driving through the neighborhood when a dog runs out in front of you, or you're driving somewhere in the neighborhoods. Things are far more complicated. Trying to have the robot or the car identify what's out there, what the obstacles are, and make decisions is really going to be the hardest part. And we have to get there sometime, eventually, I believe. Yeah, that's a great question. Computers use the answer is how is there a connection between the power demanded by the computers and the computers? The computers are starting to use a huge amount of power. For example, the supercomputer in the year 2000 ran about 1 teraflop, and a teraflop is a number of floating point operations. And we had it at the Livermore lab, required an upgrade from our 15 megawatt system. So we put another 15 megawatts so we can run these systems. So we had lots of watts to do that, like 30 megawatts of power for 1 teraflop. At the GPU conference last week, they talked about this desktop unit that ran on 1 kilowatt, 1,000 watts, and was 27 teraflops, 27 times as fast as our supercomputer in year 2000, and you can plug it into the wall. So they're getting, especially with the new GPU technology, they're getting a lot faster per watt. And the little board I showed ran on 5 watts and ran Unix and was just as powerful as a desktop using CPUs.
What's the most complex simulation you've done?
The most complex simulation I've done? Probably the hypersonic fluid dynamics. So in fluid dynamics, you model mass, momentum, and energy. And when you get to supersonic, then you worry about shocks. When you get to hypersonic, you're moving so fast that you compress air to about the density of water. And when you compress air, what happens when you compress a gas? It gets really hot. It gets screaming hot. It gets so hot that you start ripping the molecules apart. And now you get all these ions you have to track. And it becomes very bright, like a meteorite coming out of the sky. And now you have to have that radiative transfer too. So you have to think about the light coming off as heat quite a bit because it's glowing. It's a plasma now. So that's probably the most complicated thing I've worked on so far.
Speak about additive manufacturing and maybe the limitations or potentials.
Yeah. So in fact, I was fortunate to work on a 3D printing project at the lab for a year before I went on sabbatical. And we have 3D printers that are about the size of a Volkswagen bus. So they cost about $1 million to print metal. And so we bought 2 of them. And why buy one for $1 million when you could buy 2 for $2 million? We're actually using laser to sinter metal and build metal parts. And so we built a rocket motor while I was on the project. And the rocket motor was 8 inches in diameter, 11 inches high, and had skin about as thick as about a quarter inch thick, but that was hollow. And so the fuel actually went through the skin to cool off the rocket motor, actually going up, to cool off the rocket motor and preheat the fuel in order to be more efficient. And wow, I might even have an image of that I could show you real quick. So this is a talk I did for Modesto Junior College. And so here, that's the image of the rocket motor that we printed out of metal. And so you could see from the design, this is where the fuel comes out, the flame comes out. This is where the fuel goes in. The fuel goes around here and through the skin, and it travels back through, and it comes back in and reignites, or ignites at that point.
So you're saying this is metal. What state is the metal before the lasers?
Yeah, so he's asking about the state of the metal. What do we start with raw material? So we start with a fine powder, and the powder is about 30 micron in diameter. And speaking about simulation, so we're using our supercomputers to simulate that. So we take the powder, which is in these spheres, and we apply the laser to it. It melts, it flows, cools down, and resolidifies, and that makes 1 pixel for our printer. So that's or 1 voxel is the word that we use for 3D printing. So it's equivalent to the pixel size. And this is about 100 micron by 100 micron resolution of our simulations that we're doing on the supercomputer. Eventually, we want to use a supercomputer to model all of the 3D printed part so that we understand the residual stresses and the material properties in there. So we are using not only exploring 3D printing to understand how to make very cutting-edge parts, but we also want to understand how to use our supercomputers to simulate that, to improve on the process. So thank you for that question. I just happened to have the right material for that. Question way back there.
This may be out of the realm of the whole discussion and everything about future prospects of robotics and things like that. But what I'm concerned about is the future societal impact machines may have on economies and on governments in the future.
Yeah, okay. So the question was about the social implications of that. And of course, this is the reason some of these movies are supported by the Sloan Foundation. What are the social impact, the economic impact of new technologies? And so we have seen that computers have had a huge positive impact on our economy. The United States economy has been buoyed by the fact that we use computers to make things more efficient. We can get a piece of postage across the country for pennies because we use computers to do this instead of relying on people. And you'd think, well, it's going to put a lot of people out of jobs, but that hasn't happened. Those jobs they're different kinds of jobs. They're less menial labor and more programming. Of course, if you look at the difference between the people who know how to use computers and the people who don't, there's a big economic difference there. And so that's why I do a lot of the outreach I do, is trying to encourage students to think about using computers and robots and 3D printing to use those technologies, to learn about those technologies, and apply them to what they want to do, whether they want to be physicists, engineers, or architects, or whatever. I hope that answers the question. I mean, it's a huge topic, and I hope I touched it. Yeah, all of it. The question is, what kind of math do you need? And so the smart aleck answer was all of it. I think calculus is very important, and so I always advise kids to get on the track to do calculus in high school. Once you learn calculus, so many things open up to you. Of course, all math is good, but more the better. Math is really the language of science, and it's the language of computers. You know, computers think mathematically. They don't. Of course, now they're starting to learn natural languages. They're starting to interpret. You know, I can talk to my computer, like to get here. You know, the State Theater, Modesto, California, and it gave me directions the whole way, right? But math is super, super important for working with robots and computers. Yeah, I could try, and meanwhile, Joanna will.
Yeah. So one of the things that's so nice about bringing these programs out into the community, especially all the way here in Modesto, is you get to see what's going on at the lab. So for those of you who may be familiar with the lab, and I know there's a lot of students in the audience who aren't, you know, there's a fence around this big compound. And it was a naval yard 60 or 70 years ago that the government repurposed for a national research laboratory. And the public really doesn't get to go in because of the type of work that's done there, but we get to come to the community and bring things like the 3D printing to you and show you the big machines or show you some of the science that's being done that doesn't always make the public press, right? Makes our scientific press, but doesn't always get into the newspaper just because it's not all-consuming all the time. So I hope that you enjoyed it. And Vic has been on so many different projects. One of the things he showed, but he didn't have time in that movie to go into, was he showed the aerodynamics over that truck, if you remember. Well, Lawrence Livermore developed these air flaps that you now see on these big trucks on the highway that make them more fuel efficient because of the way they flow air around the truck. And this was a partnership with, I'm not quite sure what automotive motivator, but not everything is completely energy related or you know, not completely disclosure related, and it's apparently been an amazing, efficient thing. Oh, well, back
It's
to you.
alive. So I'm wondering if a few people want to come up, and a couple of guys come up. And this robot has been programmed to, there's stairs over here, has been programmed to follow people around. And because it sees in 3D, it can judge distance. And it looks for what it thinks are a couple of legs, and it tries to maintain a constant distance. And this is a very cheap, inexpensive robot. Okay, why don't you guys approach it, say hi. That's the front right there. Don't be afraid. You guys, come on out. Girls first, ladies first. Okay, you have to stand right in front of it, and you can't move too fast because it has little tiny wheels. And it's so funny, I took it to a school the other day, and I told people I was controlling it with my nose, and I had all these students trying to control it with their nose. And I took thousands of pictures of kids like this. Very good. Anybody else want to try it? Yeah. Just walk in front of it, and it'll identify a couple of legs and maintain a constant distance. Anybody want to do the hokey pokey with it? Come on out. You have to bow to it? No. So we can think about different applications of this, right? It could be a guard for your house. I took the vacuum out. But, you know, someday, a little stronger battery. You want to try? Can't keep up with your long legs. Very good. Well, I'm glad I was able to get it rebooted for you guys.
Thank you very much.
Thank you, guys.
Let's all thank Vic one more time for coming out and sharing his science with us today.
Great.